In this example, we're going to determine whether this improper integral on the left-hand side converges or diverges. In practice, we're just going to actually try to compute this improper integral. If we get a finite number at the very end, then it converges. If we get a plus or minus infinity, then this improper integral is divergent. So let's look at what we have. We have this improper integral from pi to infinity of e to the minus square root of x all over square root of x and integrating with respect to x. And well, in this problem, this infinity as the upper bound of integration, this is what's causing this integral to be quote unquote improper. So because of this, we're going to introduce a limit to help us out with this infinity integration bound. So the first step for these problems is introducing a limit to help us take care of an infinity integration bound like in this case, or if the integral is singular where we get a divide by 0, then we would introduce the limit as well. Nevertheless, the first step is introduce a limit. Once we've introduced that limit, then we proceed with the integration as normal. So in this case, thinking about what technique could help us find the antiderivative of what's sitting there in the integrand, trying some things out, but hoping to be able to integrate this as appropriate. The last step of the problem is we're actually going to compute the limit. But for right now, we're just going to ignore it. So for this integral that we have, just looking at this function, well, I see some square roots in that exponential. I see a square root downstairs in the denominator. It's not really feeling like this is going to help us out with integration by parts. We can try a u substitution. Again, we're trying things out. If things work, great. If not, go back and reassess. So in this case, we can let u equal a square root of x, which is equal to x to the 1/2 power. And then we can differentiate this to swap our dx for a du. So taking the derivative of u with respect to x, we get a 1/2 x to the minus 1/2 through the differentiation power rule. And now when we have that x to the minus 1/2 power, we could rewrite this derivative as a 1/2 times the square root of x. And of course, what we're looking for here is a relationship between dx and du. So we're going to go ahead and try to solve for dx in this u substitution. So multiplying both sides by dx, we get du is equal to 1/2 times the square root of x dx. And then now solving for dx by itself, we can multiply both sides by 2 square root of x. And we get dx by itself. So we can substitute all of this information into this improper integral. So let's see what we have. So the limit comes along for the ride. The integration bounds we can just keep with respect to x for right now. Let's change what's in that exponential. So we have e to the minus u. I'm actually going to keep that square root of x downstairs for right now. We could have also equivalently written that as a u at this point, but we can just leave it as x, because looking ahead in a moment, when we substitute in dx for du, we're going to be able to cancel out that square root of x with the square root of x in the denominator. So swapping in again the dx for du, we're going to get this is times 2 square root of x du. And we can see some cancellation here. Like I said, those square roots of x will cancel out. What this integral will equal to is, well, we still have that limit that's hanging out with us. The definite integral from pi to c. We have a factor of 2, which I'm just going to bring in front. And then finally, we have this e to the minus u du. And at this stage, we found something in the integrand that we can directly integrate. So let's go ahead and integrate this with respect to u, of course. So the antiderivative of e to the minus u is a minus e to the minus u. And now remember, we are going to substitute in those integration bounds but those integration bounds are with respect to x. So we have to be a little careful because at this point, we still need to resubstitute what we called u as the square root of x into this antiderivative. So we can write this as minus 2e to the minus, and again, going back to our u substitution, everywhere there's a u in this antiderivative, we can replace with the square root of x. And we want to evaluate that at x equals pi and x equals c. So next we can substitute substitute those integration bounds into this antiderivative. So we still have that limit as c goes to infinity. We have not touched that limit yet. We will in a moment, of minus 2, substituting in the upper bound, we get an e to the minus square root of c minus e to the lower bound, which is e to the minus square root of pi. So we've substituted in the upper bound, subtracted off the antiderivative, evaluate at the lower bound. Now we get to look at this limit. And before we look at this limit, let's just notice a couple things here, that the only c dependence in this statement is in this first term, this e to the minus square root of c. This second term, this is an exponential raised to the minus square root of pi. At the end of the day, this is just some number. That's not going to determine whether or not this is convergent or divergent, or an infinity plus minus infinity. This is just going to be some number for us. So that just is what it is. So let's take a look at this limit now. Well, we have this decaying exponential. As c goes to infinity, what's inside of that square root is going to get larger and larger and larger. And because this is a decaying exponential, this is going to go towards 0. But let's do this in another step, okay? We know that this is going to head towards 0, at least that e to the minus square root of c term. But let's rewrite this algebraically to cy. So we have the limit as c goes to infinity of minus 2. And we can rewrite these decaying exponentials because of those minus signs as a 1 over e to the square root of c minus a 1 over e to the square root of pi. Just using a little bit of algebra. Now as c goes to infinity, we can see, well, that square root of c, that's going towards infinity. So what this term really looks like for us, this is what I'm thinking, this looks like a 1 over e to the infinity. E to the infinity is some ginormous number. 1 over a huge number that's only growing and growing and growing. This thing looks like 0. So overall, at the end of the day, this looks like minus 2 times a minus 1 over e to the square root of pi, where those minus signs cancel out, and we get that this is 2 over e to the square root of pi, some number. And because this is a finite number, we can call this improper integral convergent. So if we're to backtrack a little bit with these improper integral problems, the first thing we really do is introduce a limit to help us handle, in this case, an infinity integration bound, or to handle where the integrand becomes singular, where we get to divide by 0. That second thing was not the case in this problem. We integrate as normal, kind of just ignoring that limit that's sitting out in front. Once we have the antiderivative, we plug in the integration bounds. Again, that limit is still sitting out in front. And the last thing we do is compute the limit at the very end of the problem. And if this limit is a finite number, the improper integral is convergent. If it's a plus or minus infinity, the improper integral is divergent.